Welcome to tutorial 4. In this session we will discuss solutions of 3 problems based on lectures 8 and 9. Determine the linear independence of the vectors 1 2 2 1, 1 3 3 1, 1 3 2 1, 4 1 2 2 and 5 2 4 3 in C1 cross 4. So take these vectors as rows of a matrix. It will become a 4 by 4 matrix, and then compute its row reduced echelon form. The row reduced echelon form will be of the form 1 0 0 1 by 3, 0 1 0 0 0 0 1 1 by 3, and last row all entries are 0. So this shows that the first 3 rows are linearly independent and the 4th row is a linear combination of the first 3 rows. We have not, one can arrive at this without doing any row exchanges. So therefore this is the first 3 vectors are linearly independent, and if you take the collection of all these 4 vectors, this is a linearly dependent set. We can also use this. We can also do this in another way. The way where the vectors can be taken as column vectors. So rank, as we know, is equal to the number of linearly independent rows. That is also equal to the number of linearly independent columns. So to check the linear independence, we can take this as vectors as columns of the matrix, and then apply row reduced elementary row operations to bring it to row reduced echelon form. So when you take these 1 2 2 1, 1 3 2 1, 4 1 2 2 and 5 2 4 3 as columns, then the row reduced echelon form will be of the form 1 0 0 2, 0 1 0 minus 1, 0 0 1 1 and 0 0 0 0. So of course here also what we get is that the rank is 3, therefore the number of linearly independent rows is 3, which is equal to number of linearly independent columns. So the first 3 columns are linearly independent, and the third column is indeed a linear combination of the other 2. And in this case what we get is the 4th column is equal to twice the first column plus the second minus the second column plus the third column, and that's the same linear combination that we get in the matrix, the vectors, the same relation we get among the vectors. So these 4 vectors are linearly dependent, first 3 vectors are linearly independent. Determine the linear independent vectors so that the linear combination of which is this set. So U is all A, B, C, D, E with the property that A is equal to C equal to E and B plus D is equal to 0. So we need to find out vectors in U which are linearly independent and whose span is equal to U. So first let us write U in an appropriate form. So U, I can write it as A, B, C, D, E with the property that A equal to C equal to E and B plus D is 0. So now instead of C and E I write A, and instead of D I write minus B. Therefore U can be written as A B A minus B A. and AB varying over whole of R. But this vector I can write it as this vector ABA minus BA, I can write it as A times 1 0 1 0 1 plus B times 0 1 0 minus 1 0. So every vector in U can be written as A times 1 0 1 0 1 plus B times 0 1 0 minus 1 0. That means it is a linear combination of 1 0 1 0 1 and 0 1 0 1 0 1 0 minus 1 0. So therefore U is equal to the span of these two vectors. Now we need to verify whether these two vectors are linearly independent. Now if I take these vectors as rows of and form this matrix 2 by 5 matrix, we see that these two vectors, this matrix is already in row reduced echelon form. Therefore and the rank is 2. Therefore these two vectors are linearly independent. So these are the two vectors that we were looking for. Suppose you have a matrix A which is of order m by n and it has rank R. Then show that rank of A, that means R, is less than or equal to minimum of m and n. Rank of A is the number of pivots in RREF. Now in each row there can be one pivot, at most one pivot, and in each column also there can be at most one pivot. So this says that rank of A is at most the number of rows, and at the same time rank of A is at most the number of columns. Therefore rank of A is less than or equal to m, as well as rank of A is less than or equal to n, which means rank of A is less than or equal to minimum of m and n. So this concludes tutorial 4.